Hi there, I'm Baylor Fox-Kemper. I'm one of the co-chairs of the Ocean Model Development Panel, together with Sarah Nicholson. We're actually exchanging chairs. Juliana Same has rotated off. Alistair Adcroft is rotating in. So there'll be some changes if you're getting in contact with folks soon. We have an upcoming workshop that I'd like to let you know about. If you're interested in linking filaments and fine scales, kind of 1 to 100 kilometer scale with climate change, this is the meeting for you. It's at the end of August in a variety of venues. So what do? Our greatest hits really involve forced ocean ice reference experiments where we compare different models, different numerics, different parameterizations with the same surface forcing and try and suss out the differences between the models and understand them. Recently, we've actually been worked on cloud-based frameworks for intercomparing sub-mesoscale permitting realistic ocean models. So that's extremely high resolution, very costly models. Comparing them is very difficult because it's hard to move the data set. So using the cloud to do that is great. And then we did some basic dynamics work. And then we also do examples of model hierarchy systems like this, Viking 20X, where there are nested models that zoom from coarse resolution all the way down to very fine and compare the phenomena as it becomes resolved. So when we jump over to deep ocean questions, the kind of things that we're interested in is really how do you spin up a model? How does it take? How long does it take? Can you speed it up? All those kind of things. We have an ongoing collaboration with the working group on numerical experimentation on how to spin up ocean models. In that case, think about the seasonal time scale, where you really want to get the key upper ocean dynamics leading the predictability. However, one of the difficult aspects of climate projections from going to longer time scales is getting the vertical structure of the stratification right. That can be biases in the surface, biases in the mesoscale transport, biases in the too little vertical resolution. All those things can impact getting the vertical stratification right. And interestingly, high resolution models spin up differently from coarse ones. So that makes it particularly difficult to think through about this. When we go to long horizons, it's unclear how to spin up models efficiently enough to get these issues resolved. And so we're really thinking about initialization, good data, trustworthy data. Can we tune models to reduce model drift after initializing with good data? Those are the kinds of things we really could work together with to understand better. Here's just a quick example from the Sugino et al. Paper where we ran a bunch of different models forced with the Jerry Gogo dough forcing product. And you see that from the 2000 meter to the bottom, there's a substantial drift in the multi-model mean, but also in the individual models. This makes it extremely hard to understand what's going on and extremely hard to spin up the models. It takes hundreds of thousands of years to do so. Worse yet, if we jump to a comparison between high resolution models here in red and solid lines, and then in dashed lines, low resolution models with the colors matching for the same model family, you can see that the high res and the low res model don't really trend in the same direction when we're looking at all depth temperature and all depth salinity. They can differ quite substantially. That's true in the upper ocean, it's true in the mid-depth ocean, and it's true in the deep and abyssal ocean as well. When we think about very long timescale projections, like 10,000 year kind of simulations, like these from Clark et al., the kind of drift we're talking about amounts to pretty substantial amounts of sea level rise mismatch, 2.6 meters or so over 10,000 years. And the last thing of interest for us is there's a dynamical question about when we do resolve those eddies, what should their vertical structure be? And this recent paper by Location Grosskamp really showed that it really depends sensitively on what kind of conditions you think of at the bottom. So stratification at the bottom boundary layer, how rough the bottom is, all the topographic interactions, all of that can make the modes of the eddies quite different, where they might have a zero projection, kind of very small amplitudes at the bottom, or they might have an amplitude which is opposite in sign to the surface. Thank you very much.